This is Factory World, taking you inside the construction of the $15 billion Channel Tunnel, step by step.
At sunrise, the English Channel appears calm and peaceful, but beneath these waters lies one of the greatest engineering challenges ever attempted. For centuries, this narrow sea divided two nations, separating people, trade, and cultures by nothing more than water. To build beneath the seabed, engineers first had to map the ocean floor in extraordinary detail. Below the seabed, they discovered chalk marl, strong, stable, and perfect for tunneling deep beneath the sea. Sonar scanning revealed hidden dangers beneath the ocean floor, exposing faults no human eye could see. Seismic surveys measured underground vibrations, helping engineers predict how the Earth would react to drilling. From these studies, a precise underground route was designed, threading safely beneath the English Channel. Every millimeter mattered, as two nations planned a tunnel that had to meet perfectly underground. Rock samples were carefully analyzed to ensure the tunnel could survive pressure, water, and time. At extreme depths, ocean pressure can crush steel, forcing engineers to test materials far beyond normal limits. Every material was tested against saltwater corrosion to ensure the tunnel could survive for decades beneath the sea. Engineers also had to protect marine life, carefully planning construction to minimize environmental impact. The idea of an underwater tunnel began as fragile sketches once considered impossible dreams. For over a century, visionaries imagined crossing beneath the channel, but technology always fell short. After decades of debate, governments finally approved the most ambitious underwater project ever attempted. With a budget of $15 billion, the world committed enormous resources to make the tunnel real. Engineers from multiple countries joined forces, united by a single goal beneath the ocean. Along the coastline, massive construction sites emerged, signaling the beginning of a historic effort. With the first tunnel portals carved into the earth, the journey beneath the sea officially began. The tunnel boring machines arrived in pieces, each component weighing hundreds of tons and engineered with extreme precision. At the front of each machine was the cutter head, designed to grind solid rock deep beneath the ocean. These steel teeth slowly crushed the chalk marl, slicing forward millimeter by millimeter. Lowering the machine underground was an operation of absolute precision. One mistake could halt the entire project. As the machines powered up, the underground excavation officially began. Hydraulic systems generated enormous force, pushing the machine forward through solid rock. Slowly and relentlessly, the machines drilled through the chalk beneath the seabed. Excavated rock was carried away continuously, keeping the tunnel face clear for non-stop drilling. A slurry system flushed broken rock out of the tunnel, preventing dangerous buildup underground. Laser guidance kept the machines perfectly aligned, essential for two tunnels to meet deep beneath the sea. Inside the machine, operators monitored every movement, guiding the drill through darkness with digital precision. Computer systems tracked alignment constantly. Errors of even a few millimeters could prove catastrophic. Dust suppression systems protected workers and equipment as drilling continued around the clock. Behind the machines, a perfectly shaped tunnel emerged from what was once solid rock. Regular inspections were critical, as worn components could slow progress or cause dangerous failures. Damaged cutting tools were replaced deep underground, keeping the machines operating at peak performance. Day and night, crews worked in shifts, advancing the tunnel without stopping. Progress was slow but constant, each day bringing the tunnel closer to completion. Two main tunnels were drilled in parallel, along with a central service tunnel for safety. Emergency drills prepared crews for the worst: fires, floods, or sudden pressure changes underground. The machines advanced just meters each day, demanding patience, precision, and relentless control. Rock pressure was constantly monitored to prevent collapses beneath the ocean floor. Sensitive instruments detected even the smallest vibrations deep within the surrounding earth. Bright lights cut through the darkness, revealing the rock that stood between two nations. As the distance closed, tension rose. Both tunnels had to meet with absolute accuracy. From the British side, the tunnel pushed steadily toward the center beneath the sea. From France, another machine advanced toward the same invisible meeting point. Only millimeters of rock remained between history and failure. In 1990, the impossible happened. The Channel Tunnel was finally connected beneath the sea. Steam curing hardened the rings faster, locking in strength before installation underground. Every ring was pressure tested to confirm it could survive decades beneath the sea. Completed rings were transported deep underground, following the machines that carved the tunnel. Robotic arms assembled the rings with millimeter accuracy behind the boring machines. Special gaskets sealed every joint, preventing seawater from ever entering the tunnel. By adjusting ring angles, engineers shaped the tunnel's curve deep beneath the ocean. Once assembled, the tunnel walls formed a reinforced shell strong enough to resist immense ocean pressure. Grout was injected behind the walls to fill gaps and stabilize the surrounding ground. These pumps ensured no empty spaces remained between the tunnel and the earth. Advanced scanners checked the tunnel for hidden cracks or weaknesses. Precise measurements confirmed the tunnel's diameter stayed perfectly consistent throughout its length. A smooth interior surface reduced air resistance and simplified long-term maintenance. A separate service tunnel was built to provide access for maintenance and emergencies. Emergency cross passages allowed rapid evacuation and rescue if ever needed. Fire-resistant coatings added a critical layer of protection deep beneath the sea. Acoustic insulation reduced noise levels, protecting both passengers and tunnel infrastructure. Expansion joints allowed the tunnel to flex safely with temperature changes and ground movement. Special dampers absorb vibrations caused by high-speed trains traveling underground. Condensation control prevented moisture buildup that could damage equipment over time.